Let's start the presentation.
Welcome to the first part of this webinar about multimodal analysis of 2D materials. This talk is about 2D materials analyzed by a combination of X-ray photoelectron spectroscopy and Raman spectroscopy, where the two spectroscopic techniques are configured on the same tool. We will briefly look at the theory of each technique and what information they can give us, and then move on to some case studies of how they can be applied to analyze 2D materials. In particular, we will see the advantages of using both techniques configured on the same instrument, enabling coincident XPS and Raman analysis. X-ray photoelectron spectroscopy, or XPS, is a surface analysis technique. But what do we mean by the word surface? XPS can measure information between 0 and 10 nanometers into the surface, corresponding to the red and blue zones on the diagram on this slide. 2D materials, of course, fall into exactly this range of thickness because they can be as thin as one atomic layer or perhaps a few atomic layers. The sampling depth of Raman spectroscopy depends strongly on the material being analyzed and the wavelength of a laser used to probe the surface. In some cases, it is more appropriate to think of Raman as a bulk analysis technique. But in the case of 2D materials, because the materials themselves are so thin and they have a high cross-section for Raman analysis, the spectroscopy can also be thought of as a surface-sensitive technique. This slide shows a thermoscientific Nexa surface analysis system. The base system is a high-performance XPS instrument, but can also be configured with up to 4 additional techniques for multimodal analysis. As shown in the schematic diagram in the middle of the slide, each technique is set up to analyze the same point of the sample. For this talk, we are concerned with coincident XPS and Raman analysis. The X-ray beam and laser beam for Raman analysis are set up to focus at the same point on the sample surface. But why is coincident analysis important? XPS and Raman data are often collected on the same sample, but on different tools. In that situation, can you really be sure you're looking at the same point under the same analysis conditions? With Nexa, we can perform XPS and Raman analysis at the same point within the same analysis environment. This slide shows a brief description of how XPS works. More information can be found at the website noted on the bottom of the slide, xpssimplified.com. An X-ray beam incident on a solid surface will cause photoelectrons to be emitted from the top 10 nanometers of that surface. The kinetic energy of the photoelectron tells the analyst 3 things: the element and electron orbital from which the electron came, and perhaps more importantly, the chemical bonding state of that element. It is this ability to measure chemical state information that sets XPS apart from many other techniques. With XPS, we have photons going into the sample and photoelectrons coming out. With Raman spectroscopy, it is photons in and photons out, and we are primarily measuring transitions between different vibrational states of molecules in the sample. Raman analysis is complementary to XPS. For example, crystal structure information is available from Raman, which is not always possible with XPS. With rutile and anatase, which are different phases of titanium dioxide, for example, the titanium 2p core level XPS spectra are identical, meaning that XPS cannot easily differentiate these phases, but the Raman spectra are very different to each other, making identification of each phase straightforward. If we combine XPS with Raman analysis on the same tool, we can enhance the amount of information available to the analyst. When looking at graphene, for example, XPS can detect any contaminant material on the surface and can also detect any additional carbon bonding states. In the brief example shown on this slide, 1 atomic percent of iron was found with XPS, and this is a contaminant from sample manufacturing or storage. A high-resolution scan of the carbon spectrum with XPS reveals that as well as the expected graphene-carbon bonding, there is a small amount of ether and carboxylic carbon on the graphene surface. With Raman analysis, we can measure the number of graphene layers or the quality of the 2D material. In this case, the relatively strong Raman peak, labeled D in the top spectrum, shows shows that there are quite a lot of defects in the graphene lattice structure. Moving on to some case studies for coincident XPS Raman analysis, we begin with the 2D material boron nitride. Boron nitride can exist in different crystal phases, including hexagonal or cubic arrangements. We'll use XPS to actually locate the boron nitride film on a substrate and to obtain elemental and chemical information. We'll then use Raman for information about the crystal structure. On the left-hand side of the screen, we see an optical image of the Nexa sample platter. The platter is 60 millimeters by 60 millimeters in size. 3 copper coupons are shown on the optical image, which are about 1 centimeter squared each. The boron nitride is on the sample labeled BN3 on the right-hand side, but we can't actually see optically where the boron nitride is on the copper coupon, so how can we find it for analysis? Here we see a close-up of the copper coupons. The boron nitride is optically invisible, but we can use XPS mapping to find the 2D material on the substrate. The red dotted box on the top image shows a 1 centimeter squared area for XPS mapping. We're looking for boron nitride, which can be mapped using either signals from boron or nitrogen. Nitrogen has a much stronger XPS signal, so that's preferable. The bottom image on the slide shows a total nitrogen intensity map, which seems to indicate that there is actually nitrogen everywhere. Does this mean that the boron nitride is also distributed all over the copper coupon? Every pixel in the nitrogen image has a full nitrogen XPS spectrum behind it. This means we can interrogate the data and check the spectrum shape changes due to nitrogen chemistry differences. Using principal components analysis or target factor analysis, our software can show us that there are actually 2 different kinds of nitrogen chemistry on the sample. Some areas, marked in green, have mainly organic nitrogen. The red area, however, has organic nitrogen and a nitride component, marked in red on the spectrum. If we process the imaging data, we can now see the areas of boron nitride quite clearly. Having located the boron nitride on the large area map, we can now zoom in and acquire a higher quality image over a small area. The red area on the bottom image shows the boron nitride, and the green area shows the organic nitrogen. Using XPS, we have successfully located the boron nitride, and we can acquire XPS survey data from the 2 points marked. The 0.1 spectrum from the red area has more nitrogen and a boron peak. The 0.2 spectrum from the green area does not have a boron peak. On the thermoscientific Nexa, we can also now get Raman data from exactly the same point as 0.1. This slide shows a Raman spectrum acquired from 0.1 with a 532 nanometer laser. A strong peak was observed at the Raman shift expected for hexagonally arranged boron nitride. So XPS has allowed us to find the optically invisible boron nitride and find out which elements are present on the surface. But Raman has told us about the physical structure of the 2D material. Additionally, if we perform high energy resolution XPS analysis at 0.1, we can investigate the chemical bonding states of a nitride surface. Spectra of the nitrogen and boron region are shown on this slide. Both nitrogen and boron spectra indicate that we have the expected boron nitride bonding, but we also have oxidized boron nitride as well. XPS also detected chloride contamination on the surface. This information is not easily available from Raman spectroscopy. In this example, we will be looking at coincident XPS Raman analysis of a molybdenum disulfide 2D material. Molybdenum disulfide has potential applications in the microelectronics industry, where the elemental and chemical composition and thickness of the layers will have an effect on the performance properties of the material. The Nexa optical view on the left of the slide shows a 1 centimeter squared silicon wafer piece. As far as we were aware, one monolayer of disulfide had been distributed onto this wafer piece, giving a uniform distribution of 2D material all over the wafer. XPS and Raman were used to establish the spatial distribution of the disulfide and to check its composition and thickness. The molybdenum layers are optically invisible in this case, as shown by the featureless image in the top left of the slide. XPS imaging was used to find the molybdenum on the surface by collecting molybdenum photoelectrons and at the same time rapidly rastering the sample underneath the X-ray beam. The resultant molybdenum image is shown in the top right of the slide. This image shows an inhomogeneous distribution of molybdenum across the wafer piece. The 2D material was not deposited uniformly after all. The XPS image we acquired can then be used to set up two analysis positions for further XPS analysis. These points, marked 1 and 2 in the top right image, represent locations on and off an individual flake of molybdenum disulfide. A 30-micron X-ray spot was used to acquire survey data, which show all elements except hydrogen and helium at those locations. We can see from the survey spectra and associated atomic concentration table that point 2 has virtually no molybdenum or sulfur, but that point 1 has both of these elements. The overall atomic percent of molybdenum and sulfur is low because the 2D material is so thin. XPS samples down to 10 nanometer depth, so a large amount of the XPS signal detected actually comes from the silicon wafer substrate. We have seen on the previous slide some elemental information on and off an individual molybdenum disulfide flake. XPS can also give us chemical bonding information on this same flake. In the high-resolution sulfur spectrum in the middle of the slide, we see peaks at energies expected for metal sulfides. In the molybdenum spectrum on the left of the slide, we also see peaks at energies that correlate with molybdenum disulfide. However, we also see some other peaks, marked in red, that are due to strongly oxidized molybdenum on the surface, probably in the 6+ oxidation state. So at least some of this 50-micron molybdenum flake has been oxidized. If we want to measure the thickness of the molybdisulfide flake, we could use Raman spectroscopy, but it would not be possible to find exactly the same optically invisible flake if we move to another separate Raman system. With the Nexa, however, we can get Raman data from the same points as we got XPS data. This slide shows a 532 nanometer Raman spectra acquired on and off the flake we previously analyzed with XPS. At both positions, we see strong silicon peaks due to the substrate, but at point 1, we also see 2 peaks due to the molybdisulfide. The splitting between these peaks tells us something about the number of molybdisulfide layer units in the flake. The black spectrum shows Raman peaks from a big lump of molybdisulfide as a reference. The splitting between peaks in that case is 26 wave numbers. For the spectrum at point 1, however, the splitting is 18 wave numbers, indicating the flake has a single unit layer of molybdisulfide. This is information that would be difficult to measure with XPS. By using coincident XPS and Raman analysis on the same tool, we have analyzed the elemental and chemical composition of a 50-micron flake of molybdisulfide, but we have also measured its thickness with Raman spectroscopy. In this presentation, we have seen how the thermoscientific Nexa can be configured with multiple analysis techniques, all looking at the same location on a sample. When using XPS and Raman together on the same tool, we can expand the amount of information available to the analyst when looking at 2D materials. Quantifiable elemental and chemical bonding information from XPS can be combined with structural information from Raman spectroscopy. Thank you for your attention on this part of the webinar, and please feel free to contact me at the email address given on this slide. I'd now like to hand over to my colleague Matthew, who will continue to tell you about Raman and XPS analysis of 2D materials.
Thank you, Paul. My name is Matthew Cole. I'm the Raman Spectroscopy Product Manager at Thermo Scientific, and I wanted to quickly add one additional example of how XPS and Raman can give complementary information on advanced 2D materials. One significant area of interest where XPS Raman systems are useful is for examining carbon nanomaterials. Graphene, as we are all aware, has special and desirable physical and electronic properties. These properties are, of course, related to the quality of the graphene structure and are impacted by the number of layers, defects, the presence of other functional groups, or other deviations from ideal structure. Therefore, holistic characterization of these materials is critical. Raman and XPS together can determine properties such as layer thickness, morphology, chemical modification, and others. Here are examples of typical spectra we achieve with XPS for these types of materials, graphene on the right and graphene oxide on the left. Determining between these two compounds, and therefore the oxidation state, chemical environment, or presence of these other functional groups, can be achieved readily. However, determining the sp2 and sp3 bond content, and therefore the structure, can be difficult. There is a way of achieving this with X-ray-induced Auger electron spectroscopy. This can yield an indication of the sp2 character of the material being analyzed. However, going so far as to determine single-layer versus multi-layer graphene is difficult. On the other hand, the ability to determine sp2 versus sp3 content and overall graphene material quality is built into Raman spectroscopy. The characteristic bands are shown here, known as the G and 2D bands. They are found in both graphite and graphene, but there are significant differences in both intensity ratio and peak shape when comparing these two materials. The 2D band specifically can be decomposed into multiple spectroscopic features and analyzed. A single layer, shown here in the bottom plot, shows a clean, symmetric Gaussian shape. Multiple layers show a spread out band with several underlying spectroscopic components, allowing, up to a point, the determination of how many layers are present. In this manner, XPS and Raman can be combined to give a complete look at the quality of graphene materials. For example, when looking at a carbon nanotube sample, the XPS data shows a number of elements present that are unexpected. In this case, it's residue from the production of the nanotubes. The Raman data gives information on the quality of the nanotube and the degree of defects, which directly correlate to properties like conductivity. I'd like to take a moment to point out how the studies you've seen on the previous slides have been carried out. As the world leader in serving science, Thermo Fisher Scientific offers a vast range of material analysis tools and instruments, including those for multimodal and hyphenated techniques. The Thermo Scientific IXR Raman spectrometer is a full research-grade Raman spectrometer in a compact footprint, Raman in a box, if you will, designed specifically for hyphenated integration into multimodal analysis setups. It is available today with several of our material characterization instruments as a complete multimodal solution, including XPS, as you've seen here, as well as rheometers and extruders, opening the door for multimodal analysis of a wide range of materials. It is now my pleasure to hand the presentation over to Dr. Min Wu, electron spectroscopist at Thermo Fisher Scientific, who will discuss the characterization of another important class of 2D materials.
So thanks to Matt's introduction. In this session, we will discuss how to image beam-sensitive metal-organic frameworks in another common term, MOFs, in Spectra TEM platform. The benefits of Spectra is that it provides us the highest throughput by Spectra 200 and highest resolution by Spectra 300 down to sub-angstrom scale. We also can combine the high sensitivity Panther STEM detector and the revolutionary IDPC technology to image beam-sensitive MOFs with extremely low-dose electrons. Here is a comparison of HAADF images with different probe current with Panther STEM detector. We can still obtain very high-quality STEM images with extremely low-dose electrons, less than 1 picoam probe current, and low dose means low beam damage to the sample. The Panther detector itself actually has single electron sensitivity. We can combine the capability of Panther STEM detector with our revolutionary IDPC technology to obtain even better images for even less dose. Here is the comparison of HAADF, ABF, and IDPC images at an electron dose of 12,000 electrons per square angstrom. This amount of dose is already pushing the limit of ABF image. You can see that in the image, the middle one has too much noise and is losing the resolution. But with IDPC, we can maintain excellent signal-to-noise ratio and still have very high quality STEM image, as you can see from the right-hand side image. So combining IDPC technology and Panther STEM detector, we can image very light elements with extremely low electron dose. Here is an example of MOF UIO66, imaged with only a dose of 166 electron dose per square angstrom. We can enlarge the image and see the benzene ring. Here we can see the benzene rings, as you can see now from the screen. And it's actually the first time in history that people are able to observe these benzene rings in STEM mode. Let's have a look at another example. The sample here shown here is MOF MIL101. And the images were taken again by Panther STEM detector using IDPC technology. We can obtain very high quality STEM image of the structure using 96 electrons per square angstrom, as you can see from the left-hand side image. And we made another scan, then the electron dose was increased to 192 electrons per square angstrom. And you can see the outside of this sample is already curving. That's shown in the middle image. Then we made a third scan, and in the right-hand side image, you can see already the sample is being destroyed. So this is how sensitive MOF samples are actually prone to beam damage. Very, very easy to get damaged. Here are some STEM images of MIL101 MOF sample with even lower dose. The electrons we used are only 42 electrons per square angstrom. We can see the metal and organic framework with unprecedented resolution and contrast thanks to Panther STEM detector and IDPC technology. So all in all, Spectra is ideal for atomic resolution imaging of beam-sensitive MOFs. We have extended accelerating voltage from 30 kV to 300 kV. We can image with a large range of electron dose from dozen electrons to 100 million electrons per square angstrom. And we have unprecedented Panther STEM detection system and groundbreaking IDPC technology. We combine these two and enable a low dose, high sensitivity, and damage-free image of MOF samples. With this, we conclude the multimodal analysis of 2D materials session. Thanks very much for sticking with us to the end. And if you need any more information regarding the platforms, Raman systems, XPS systems, or electron microscope systems, please feel free to go visit us online, and you could find all the portfolio, the products are all there, all the information you need. And if you have any more questions, please feel free to type in, and we will discuss them during the question and answer session.
Hello, everyone, and thank you very much for joining the session today. I would like to open the Q&A session by thanking our presenters and for the insight which they gave us into the topic of multimodal analysis of 2D materials. We are now starting a 10-minute Q&A session, so please feel free to send your questions, and we will try to answer them in 10 minutes time that we have available. Without further ado, the first question, what is IDPS?
Hi, this is Min. So what is IDPC? IDPC is a technology. It's short for Integrated Differential Phase Contrast. It's a special STEM imaging technique. And using this technique, and it's patented and only owned by Thermo Fisher Scientific. And we use this technique, we could enable live imaging of the phase of transmission function of this, in TEM. So we can use very low electron dose and to image light elements and heavy elements at the same time. But we only need a very small dose of electrons, as I just shown in the presentation. But we could image carbon and oxygen and everything together with heavier elements. And the signal-to-noise ratio is really good. So it has a significant advantage for beam-sensitive 2D materials, and especially in TEM. And can I follow the question? Is it possible to use IDPC technology in already existing systems such as Talos system? And the answer is yes. So it's a technology, and we support it with of this technology on all the Talos systems and all the Spectra systems, and also metros if it's in semiconductor.
Great. Thank you, Min. Going to the next question. This one is about Raman, and the question is there any database available for Raman analysis?
Yeah, absolutely. This is Matthew speaking. So the Omnic spectroscopy workstation that is used to run the Raman components can be loaded with several libraries from the factory. We have available materials characterization libraries, which are very relevant for this topic. We also have condensed phase, organics, polymers, many other types. You also have the ability to add and curate your own spectra to libraries for use during the course of your investigations.
Great. Thank you. Another question is it possible for XPS to reveal chemical structure of MOFs, such as oxidation state and electronical structure?
Hi, this is Paul, and thank you for the question. Yes, it is. So we actually looked at a copper metal organic framework sample recently, and we were able to work out that it was a copper 2+ oxidation state. And when it comes to electronic structure, XPS can give quite a lot of information about that. So, for example, if you're looking at the valence band portion of the XPS spectrum, you can work out what the valence band offsets are. And in some materials, you can measure the band gap, for example, using XPS or related techniques. So yes, the answer to that question is a definite yes.
Great. And another question about laser. Can we use multiple lasers? And is the laser power tunable?
Yes, we can. So referring specifically to the example in the presentation with the combined XPS Raman system, we can provide, I think, 3 lasers. So green, red, and blue. So 532 nanometers, 785 nanometers, and 455 nanometers. And obviously, for example, those different wavelengths will give you, in some cases, it might be fluorescence on a sample, and by changing the wavelength of laser, you can suppress the fluorescence. That's definitely possible. And yes, you can change the laser power as well. So that's continuously tunable between limits, basically.
Thank you, Paul. The next question, can we use STM for polymer nanocomposites? And if so, does it require conducting coating layer for the electron?
I guess that's the question for me. Thanks for asking. Yes, we could use them for polymer nanocomposites. And no, so a lot of our materials we deal with is not very conductive. like this metal organic framework. So we do not require a coating layer for the electrons, because if you have a coating layer, the sample is in a transmission mode, then we would have interference for this coating layer. Then we will not be able to see the structure very clearly, and especially you go down to atomic level. So we have a lot of different techniques to reduce the charging effect, and so we do not require the coating, and we use different techniques. We can use the low beam energy, low dose electrons, and we still can obtain a very good image of the samples.
Clear. And another question about STM right away. What model of STM was used to take low dose IDCP images on slide 4 of the presentation?
In slide 4, for the benzene ring, I guess, so all the images I showed in this presentation are taken on Spectra system, and the Spectra 300 specifically.
Clear. Thank you, Min. The next question, besides viewing the benzene ring system, is it possible to also view organic structures or intermolecular bonds in inorganic materials?
They're all technically possible. We could try. It will not be easy to image these bonds. What we can do is to use IDPC and the very high sensitivity STEM Panther STEM detector, and we could image. You can see the atoms, and in this method, we will not be able to directly tell you what sort of phase they are, particularly, but you will be able to see them. But it can be challenging, but it's achievable.
Right. Thank you, Min. The next question is about Raman. So since Raman is the photon in, photon out technique, what is the maximum sampling depth?
Sure thing. This is Matthew. So this particular implementation, the combination of XPS and Raman, uses a relatively low power magnification objective to do the Raman sampling. I don't know the exact number off the top of my head, but this would be in and around the range of 10 micrometers or greater. It's certainly going to be much larger depth of penetration and depth of measurement than the XPS component.
Thank you. The next question, what are the sample preparations required to image the MOF in high resolution TEM?
I think that's the question for me again. So the sample preparation, we usually, for these MOF samples, we grind them into powders and put them in a liquid, and then dip this liquid with, it's a suspension. We dip it to a TM grid on sort of a support, and we image it. So sometimes the samples come from like in powder form coming from customers. Sometimes they send us this MOS formulated form MOS, and we just ground them, and then we prepare it using the same way.
Yeah, thank you, Min. The next question is it possible for IDPC to resolve light element dope or heavier element, or vice versa?
Yes, it is possible. Sample prep, as I said, it would be quite crucial. But then in the STEM mode, we could go down really to see them as things we can image both light and heavy elements at the same time. And if they're resolvable, it depends on which orientation they are arranged, like what kind of order they are arranged. And we, of course, you need to tilt the sample quite a lot to find a good orientation that you can, clearly see the different atoms. But yeah, it is possible.
Right. Thank you. The next question, I think it goes to Paul. What are the relative probe spore sizes for the XPS and Raman?
With the XPS of a Nexa, for example, the X-ray spot can go from a 400 micron size all the way down to a 10 micron size in 5 micron steps. The Raman spot is somewhere around about 15, 20 micron diameter. So the Raman spot is basically about the same size as the smallest X-ray spot, but the X-ray spot can also be larger on that system.
Right. And does the Raman option have to be bought with the system, or can it be upgraded later on?
The nice thing there is if you buy a Nexa, just a basic Nexa, you get XPS, and then if you want to, you can either buy the Raman with it, or you can wait and upgrade it at a later date.
Great. Thank you. One of the last questions, as we are running out of time, what is the advantage of Panther STEM detector?
Okay, I guess this is a question for me again. Panther STEM detector is our newest generation STEM detector. So it has it's very sensitive, and it has a single electron sensitivity. And we also have other modes that could. So, for example, if there's only one electron, we can detect it. But then if there's a lot more electrons, we can also detect it. It has a really large sort of dynamic range. But of course, if you combine it with IDPC, then we care a lot about the sensitivity of it. You know, the ability to detect very low dose electrons.
Right.
Yes. Thanks.
And the last question, is it possible to use SERS with XPS?
Sure thing. So SERS in this case is a surface enhanced Raman spectroscopy. And at a high level, the answer would be yes, you can take your sample and dope it with either SERS active nanoparticles or some sort of SERS active surface. That's sort of the requirements for getting SERS enhancements, and you choose a proper Raman wavelength. Now, do be aware that these materials that you must add to your sample will, of course, impact your XPS measurements. They'll appear. So it's very important to keep in mind how that's going to impact the whole experiment to get this Raman enhancement.
Great. Thank you very much, Paul, Min, and Matthew. Thanks a lot for the insight. I'd like to invite those people visiting the session to go and visit our virtual booth or the networking lounge before the next session starts. And I'd like to thank you all for joining us today. Thank you very much, and we are closing the session.